All right. Just some reminders. Stay engaged with us at seattleastro.org. That's a place where we're going to have some updated all of our content on there. So stay engaged there. RSVP to events. You can join. We have a Facebook page. We're also trying to keep that very active. We have a Twitter, so y'all can follow us on Twitter. And if you have any questions about SAS, we have an outreach group, and right now it's being led by Wendy. So just email us at outreach@seattleastro.org. And we do have some equipment rentals that right now that's a very popular feature of SAS. So you can connect with people if you're looking into trying out equipment and things like that. There is a bit of a wait list right now, but feel free to reach out anyways. We'd love to see people staying engaged in different ways. Let's see. And then some upcoming events really quick before we go to breakout rooms. Like I said, Thursday, we are having the Mars landing, so make sure you stay tuned for that and watch that live. It's going to be a great time. I'm excited for every month SAS has an astrophotography special interest group, and so that is going to be on the practical considerations of choosing an imaging camera. So that's going to be a lot of fun, and it's built for experienced and new people. So no matter what your level is, I think here at SAS, we want to make it accessible and to anybody, those of who are just interested and don't know anything, or those of our experts. We want to bring our people together. So we have the astrophotography group meeting on Tuesday, the second Tuesday of every month, or the first Tuesday of every month, sorry. Or maybe it's the second. You get that one right. But yeah, Tuesday, March 9th, yeah. And then I am super excited. On March 17th, Phil Plate, many of you know him as the Bad Astronomer, aka he has a very popular PBS crash course. It's on YouTube for free. It's like 10-15 minute segment videos, very easy for experienced people to digest, and also younger audiences, newer audiences. That's great. And around March and April, we're going to start looking into, based on state regulations, how to safely do some social distancing activities. So be on the lookout for that. We're planning that. So I know we're in a very virtual world right now, but we want to mix and find the right balance between safety, virtual, and in person as the weather gets better and we read the scene. So, and one thing that we definitely want to highlight is that a great way to stay connected is volunteering, and volunteering is key to keep this group alive. I'll just say that everybody you see on screen today, outside of our printers, we're all volunteers, and so you can be a part of this too. And if you take one thing home today, it's going to be that this is about community, and this is your SAS. So if you have any ideas or anything you want to share, just reach out. We'll find a way to connect with you. It might take us a couple of days, but we will respond to all the emails that we get. So that's something to always keep in mind. And so we can, there's outreach opportunities right now. There's virtually where we're going into different communities and, and sharing about our programs. Star parties, that's a popular thing for us. Like I said, that's going to be regulation dependent, but we are looking at ways to do that safely this year. We're working on compiling a stargazing list site for observation locations. So if you want to be a part of that, getting information and sharing information, that's a great way. Co-hosting meetings, introducing speakers, that's another great way to get connected. Equipment rentals, we have an equipment rental opportunities, and if you're looking to help out with that, there's ways to get engaged there, and also you get access to some cool equipment as well. And our astrophotography group that meets once a month, they could always use some help if you're trying to help out with helping running the meetings. It's a really fun group to be a part of, and we're looking to grow that group as well too this year. Yeah, let's see. And then so we are going to be going into breakout rooms just really quick, maybe 10-15 minutes or so, and then we'll have some music. Charles will take it away. Y'all know the Melissa Rice Mars presentation. That's going to be fun. Some more music, and then we'll have a fun science and pop fiction segment. So that's going to be fun. So we get a double dose of Charles. So this is going to be great. All right. And Sierra, you can unmute yourself. Do we anything to know for the breakout rooms?
No, these are just an opportunity to kind of chat, get to know other attendees at the banquet and maybe other members as well. So yeah, you'll just be introducing yourself. There will be a host in each room. So I think we're ready to start here whenever you're ready, Aaron.
All right, let's do it.
About 100 people plus on, so this is great. I love this audience, and I was super energetic and excited about the group that we just had. Also, I'd like to share that my partner just handed me my beverage with a moon ice cube, and so I'm very proud of it. And so that's what I'll have for this evening. I'm loosening up. It feels great, and then also I'd like to. We're gonna have a great time to check in and everything. Yes, that's a great one too. And so let's turn it over to Dwayne.
Before we continue on this great journey, I would like everyone to know that we have a band tonight that is providing some great live music. And as this band is singing, the lyrics will be posted in the Zoom chat. So if you want to follow along and sing along, you'll be muted, but you'll be able to see the lyrics through the Zoom chat. So it is with great honor that I introduce our entertainment for the evening. This band has a sound like no other. KEXP radio host Evo Walker described this band's sound as PBS metal. Yes, this band has already created its own music genre. That same radio host also described their sound as a combination of Carole King mixed with Paul McCartney mixed with metal. This is a postmodern beach music family band from the great Emerald City of Seattle, Washington. And the members of this band are Jared, Dominic, and they are led by their lead singer, Julia. Ladies and gentlemen, without further ado, I present to you the band Warren Doom.
1, 2, 3, 4, 5, 6. And that cowbell is for Dwayne, who asked for a little bit more of it in sound check last week. So that's for you. And we'd like to do on these kinds of live streams, do the because we can feel your energy here, and we're just so grateful to really be playing what feels like a real show. It's so nice to be here, and I want to thank Aaron for inviting us and all the wonderful people who are a part of the Seattle Astronomical Society. And I know there's some buddies of ours, some family members of ours who are out there watching, and we're just so grateful that you're spending some time with us this evening. So thank you. What a treat. This next tune that we're going to play for you is called Count on Me, and this one is going to be on our band's upcoming LP release next month. And if you want to check out more about it, you can just follow Warren Dunes on our social media stuff. So here we go. burning, won't you learn to count on me?
Oh, I saw Charles is super excited. Yeah. Wendy, do you want to take it over?
Hi, everybody. My name is Wendy Froget, and I am the Outreach Coordinator for SAS. I hope you guys are all having a good time so far. I have the honor today of introducing our first speaker. As an astrophysics professor at CUNY College of Staten Island and an associate with the Hayden Planetarium and the American Museum of Natural History in New York, his research focuses on colliding galaxies, quasars, and the star formation history of the universe. He is the award-winning co-author of several books, including One Universe, At Home with the Cosmos, and the Handy Astronomy Answer Book. As a frequent host on the podcast and radio show Star Talk, he brings his enthusiasm for science and a love of pop culture together and has earned the title of Geek in Chief for his work on the show. Our guest today believes that educating people about the universe is central to his role as an astrophysicist. In his own words, he noted, "I don't make or build anything useful. What I contribute to society is knowledge and understanding. These are the things that enrich people's lives, no matter who they are or what they do." We're so happy that he is here today with us to share his insights into the universe. Please feel free to put any questions you might have for him into the chat to be answered at the end. So now, please welcome Dr. Charles Liu.
Hi, everybody. Hello. Thank you so much for having me. Wendy, if there's any technical issues, jump in anytime so that you can, tell me if I need to be fixed or anything like that. But I am so happy to be here. Thank you. One of those very tiny silver linings of all the stuff that's going on in the world right now is that I get to be in Seattle with you all virtually, which otherwise might be really hard, especially today, which I understand there's quite a bit of snow going on over there. We got our 2 feet or so last week and the week before, so we already know what you're feeling to some extent. But I have very fond memories of Seattle. I was there for the American Astronomical Society meeting there when my youngest child, we have 3, youngest child was still 4 or 5 years old. And we took one of the days in the middle when I wasn't presenting science to go visit, as he called it, the Space Noodle. And we went up the Space Noodle and up to the restaurant, and we had the ice cream, but it was a little bit overpriced, but still super cool because it's steaming with all the dry ice and the liquid nitrogen and whatnot it was. And then, of course, Isaac and his siblings, who are all older, 5 years, 9 years older, said, "We want to go out on the walk," even though this is January and it's 67 miles per hour according to the anemometer. And they were like, "Yeah, we want to go around." Like, whoa. And so my wife and I are watching them go, and they're like, "Ah," the classical sort of. Anyway, great memories, wonderful place, and just overall Seattle we enjoyed so much. But that's a special spot in my heart for us. So I very much appreciate having the chance to talk with you all. Thank you. I know that in this group there is a combination of people who don't have as much experience and just here to sort of learn about astronomy. And then there are some of you who may actually know even more about the universe than I do. And that's great. I'm happy to talk. My conversation today is going to be about galaxies and specifically the Milky Way galaxy to some extent, its past, its present, its future, and our sort of place in it. And so I'll do a combination of things that are both very sort of introductory, but still mind-blowing, even for those of us who have been thinking about these things for a long time, and then go on to things that are more advanced, some of the research that I'm doing in particular, which I think is very cool, thinking about what happens after galaxies collide and what that tells us about the way the universe ages. So I want you all to know how happy I am to be here, and thank you so much for your time and energy. I'm only going to share my screen occasionally and not that often, so hopefully that will be enough. I guess my video has been pinned a little bit, right? So, for better or worse, you all know that I have not cut my hair in more than a year. That's kind of a record for me. So Aaron assures me that I actually will fit into Seattle better that way than otherwise, which is cool, which makes me happy too. But anyway, any kinds of questions or comments at all, put them in the chat and I'm happy to talk about them later. My goal is to finish talking a little before 8 o'clock, so we have lots of time to talk about other things as well. Okay, so if that sounds good, let's just go right to the point. I know that later on, and I'm going to be really enjoying this as well, you're going to have a talk about Mars and what's happening in just a few days. I think that's super duper cool, right? This is the Western Mars Lab, and that's the western side of Mars, I guess. And Dr. Melissa Rice is really one of the top-notch people in the whole world about Mars. And when Perseverance lands on the 18th, I'm going to be there with bated breath. It's one of the most amazing scientific journeys that I can imagine any of us humans going to another planet. not being able to go there ourselves, but sending our robot proxies who are our eyes and ears and hands and feet so that we can see all these things. It's kind of, to me, like if I were a goldfish and I wanted to go see what's on in the other bowl. And I actually am able to launch sort of a robot fish out through the air, drones out in and lands in another goldfish bowl, and then they can explore that area and see, are there other fish just like me out there? I think that's a super, super cool thing, and I can't wait. My research is looking at things that may be a little bit more abstract than that. Imagine instead of being a goldfish in a bowl, imagine if I were a goldfish in the Atlantic Ocean. Can't see a thing, right? I look all around me, all there is water. I see lots of other fish all around. I see lots of other things, but where does it end? How far does it go? After I look for a while into the distance, things become murky because, well, water doesn't transmit light very well. Sooner or later, I wind up not being able to see. It's very frustrating, right? If I want to know what the shape of the coastline of the Atlantic Ocean is, as a goldfish somewhere around Mallorca, or pick your favorite island, I don't know. If you like St. Helena down in the South Atlantic, or if you want to go north to the Canaries, I don't mind. Just imagine being one of those distant places. How do you know? How can we figure out the way, the shape, the structure of this great big ocean we live in? That is the issue with us and the Milky Way galaxy. The Milky Way galaxy envelops us. It's a wonderful place, but it's really, really big. And it keeps getting bigger every time we measure it in one way or another. We think we've hit the limit every time we use a new technology, and then we see, wow, there's more to it. And then every time we think we've counted up the total number of stars we think there are, new technology, boom, there's more. And so how are we going to learn about the Milky Way galaxy and understand it as carefully as we can understand our own goldfish bowl, right? Well, the first thing we have to do is to look at other galaxies. The first thing we have to realize is that we are not alone in our structure. And that's a huge understanding point, right? Just as someone like Giordano Bruno in the 1600s insisted that there were other worlds like the Earth and maybe even other living things out in space, so too did we have to figure out that our Milky Way galaxy is one amongst billions out in the universe. And I think, let me just pose this question right now. Do people know whom we normally credit for deciding or figuring out or confirming to us that the Milky Way galaxy is not the only galaxy in the universe, but in fact, it is one of many? Oh yes, Aaron, thank you. 8 p.m. Eastern time. Yes, I am in New Jersey. So if I said 8 p.m. and you guys are thinking I'd be going for 3.5 hours, it's okay. It's all good. If I were going for 3.5 hours, I'd expect you to go get a drink, get some coffee, get some salmon, whatever, coming back.
Edwin Hubble.
Edwin Hubble, right, Russell? Right, Miguel? Absolutely, Mr. Edwin Hubble. Now, you've probably seen sort of stereotypical pictures of Edwin Hubble with a pipe kind of looking like this, and Edwin Hubble, looking in an eyepiece of a telescope in a black and white photo looking very distinguished. And really, because we're on Zoom, you're welcome to just pop on over on your, web page or your browser or something, just pop on over and Google pictures of oh wait, you can't Google in Seattle, you have to use Bing, right? Sorry, but in any case, go to your favorite search engine and find something like Edwin Hubble, and you'll see it. I believe you, Miguel. Bing, I suppose, is awesome. Sorry, I haven't used it very much, I must admit. I do use Outlook, so if that helps. And I suppose I have an Amazon author page, so, that's 2 to 1. Now all I just have to do is fly on a Boeing 737 MAX. And then we're good, right? But that's not happening for a little while. In any case, sorry, I keep getting distracted. This is one of my signatures. I don't know if you've all ever heard me in public. I get distracted easily. It's kind of my, oh yeah, I'll drink a Starbucks, yeah. It's kind of my signature that I'm easily distractible. In fact, I probably, if I were like growing up now instead of back in the 1970s or something, I probably would have been diagnosed with something along the lines of ADD. But that's okay. Fortunately, that didn't happen, or it maybe if it happened, could have improved my life. But in any case, I am lucky that I've made it to adulthood and it didn't harm me. And in fact, I now embrace it, and I'm just this guy that just does this kind of thing all the time. But in any case, I digress as usual. The story is basically that Edwin Hubble is a guy in America, and he went to the University of Chicago. He was an athlete and he was smart. He got a Rhodes Scholarship, went to Britain, came back, decided he wanted to do astronomy and physics for a career rather than political science or whatever else he was doing. And he wound up going to California to do work there to try to figure out whether or not the universe was expanding, or whether or not the Andromeda galaxy, this little faint little dot far away from us, this sort of fuzzy thing, is a galaxy like our own. And he did. He figured it out using a technique called Cepheid variables. At that time, and even today, it's really hard to know how far away something is out in the universe. You can't exactly run out there with a tape measure and figure out how far the sun is, right? Or even the moon for that matter. So in this case, what you had to do is to find light bulbs that were standard. Now imagine if you had a, say, 15-watt incandescent light bulb. No, that would be too faint. Let's go with the LED version. Okay, 15-watt, much better and economical and more bright in the optical. And you have a light bulb, and you knew that every single light bulb in the world was the same amount of light producing. Okay, or that you could tell based on how fast a light bulb blinks, then you would know how much energy that light bulb puts out. And so this concept of the Cepheid variable, which I will type into the chat just so if you ever want to look it up. These are a certain kind of pulsating star. Some of you know this. In fact, Polaris, the North Star, is a Cepheid variable. They are in a certain position on the Hertzsprung-Russell diagram such that they get to a point where they're unstable. They actually start shrinking because there's not enough energy inside them to be keeping them the same size. But as it shrinks, then at get to a critical point, it suddenly reignites additional nuclear fusion inside the centers and thus puffs it back out again. And then it comes back down and then puffs it back out again, and so forth in a cycle ranging anywhere from a few days per puff to a few months per puff. And a tremendously talented astronomer named Henrietta Swan Leavitt, I will type her name in as well, Henrietta Swan Leavitt, a long time ago figured out that if you could measure enough Cepheid variables, you could figure out how far away a Cepheid variable is by how bright it looks to your telescope, plus how long it takes for it to puff up and shrink back down again. So it doesn't matter whether a Cepheid variable has a twin or has a companion or not. Its own process gives you that effect. And so you wind up being able to get a lot of them together in one place, like one nebula or one blob or one part of the sky or something like that. That allows you to figure out how far away this object is. So Edwin Hubble used this Leavitt law to figure out, at that time using the world's largest telescope, which was the Mount Wilson 100-inch telescope, the Hooker telescope on Mount Wilson, to measure several dozen Cepheid variables in the Andromeda galaxy. And lo and behold, he found that the Andromeda galaxy was a whopping 2 million light years away. Now, our Milky Way galaxy, we knew wasn't bigger than about 100,000 light years in diameter. So if it were 2 million light years away, well, we're all good. That thing is huge. It's far, far away, right? And so thus it must be another galaxy kind of like ours. And so that realization led us to then examine all of the other galaxies in the universe and what they look like. And that helped us to see what our galaxy looks like. And then we had our own technology later, much later, decades later, in order to figure out what the details in our own little ocean are, even though our own goldfish bowl is so small within this vast, vast ocean. I will mention one thing just for fun, and some of you already know this, but Edwin Hubble, when he first measured the distances of his measurements to distances to galaxies like Andromeda, he actually got it wrong. The Leavitt law wasn't quite right back then, even though Henrietta Swan Leavitt got the correct sort of relationship. The actual like percentages, the constants that were multiplied by them were a little bit off because they didn't have yet a good understanding of what interstellar dust does to light as it travels through it. This is over 100 years ago, of course. So as a result, Edwin Hubble's numbers were wrong. And for a period of time, he actually got the age of the universe way wrong. But nevertheless, we still give him credit today, right? And I want to make that point to you all as we're looking at some of these things. I'm going to start showing you a few pictures and so forth. They could be wrong. We might not have things right, but as long as we scientists know we could be wrong, and we try to say, instead of just saying, it is so, we just sort of say, we think this is so, and this is why, then we can test it and figure out whether we're right or wrong, and that's okay. So for those of you who are thinking about, is science a career for me? I have had students, research students, who have been frustrated and said, I can't be a scientist. After working with you for 3 months, I've decided that nothing against you, but I can't be a scientist because there's never a right answer. I always have to tell you, I think this is what it is, and these are the chances that I'm wrong. Darn it, I want a right answer. So they go become mathematicians. Meanwhile, the people who are like, oh yeah, I can live with uncertainty. This works for me. Then they become astronomers and they revel in not knowing what the heck is going on in the universe. But that's okay, because that's, for example, my regular lot in life is not to know what's going on. But it turns out to be kind of a fun ride anyway. So let me share now, if I can figure this out correctly. As of a few years ago, what astronomers are pretty sure the Milky Way galaxy is kind of like. This is a top view here, and this is from about 2014. If everyone can see the screen, it's straightforward. You can kind of make out these markers: 15,000 light years, 30,000 light years, these sort of rings, and where everything is and how far away we are from the center of the galaxy. Notice that the coordinates of this map here are centered around us. And no, we are not in the middle of the Milky Way galaxy. We're off to the side. In fact, we are a healthy distance from the center, something like 25,000 light years. Now, that's kind of depressing. That means that we're kind of out in the sticks. Now, that's not so bad, because like maybe some of you don't live in Seattle, maybe you live in, Bellingham or something like that. That's okay. It's like we're out in the suburbs, okay? That's sort of one thing. Now, good thing we're like in Vancouver or something. That would be way off in the middle of nowhere. Wouldn't have a whole lot of stars, but we're not that far away from the edge. We're kind of in the middle, which is good. And the second reason it's good we're not right in the middle is because right in the middle is a supermassive black hole, about 4 million times the mass of the sun. And we wouldn't be very happy if we were right in that area. The discovery of that black hole and the measurement of that black hole and its motion and its mass led to the awarding this past year of the Nobel Prize in Physics to Gerhard Binzel and Andrea Ghez for their work on this. It's a tremendously interesting story, and I encourage you to look that up as time goes forward, because it's cool to know we have that black hole in the center there. But do not worry, it does not act like a cosmic vacuum cleaner. It does not suck us in. In fact, black holes don't suck. They just don't. Okay, for various reasons, both figuratively and literally, it's just a hole. So if you imagine seeing a manhole cover off of a hole in the sidewalk, as long as you don't go over there and jump in, you're cool. Just stay away from it. And we are healthily far away from that galaxy. It's okay. Now, you see that in the middle here is this thing that kind of looks like a football, right? That is what we call the bar of the Milky Way galaxy. And that's an important discovery that happened also within just the past 10 to 20 years. The spiral arms of the Milky Way galaxy, these famous structures here and here, the ones that are big, they don't start at the center where the black hole is. Instead, they start at the edge of a bar, and this bar is thousands of light years long. Remember, a light year is about 6 trillion miles, so that's a long way to go. And it's very interesting that this bar is there because it means that the Milky Way galaxy has done something interesting over the past few 100 million years. Something has hit it, something has caused it to make a strange bar shape in the middle, just not standing still like a spiral galaxy. To think about how that might work, imagine your toilet flushing. Okay, goes down in the middle. Now that goes down in a single central hole, and of course that's a drain and not a black hole with a gravitational potential or anything like that. But the basic idea is that the spiral forms because of the motion that's going around and around in the galaxy. Now imagine throwing a shoe into your toilet, and what would happen to the water, right? As it's flushing, that shoe just kind of breaks up that nice, beautiful spiral and some other structure takes place. Or what if instead of putting shoes in, what if you just poured in a whole bunch of other water as it was flushing? What would happen to the shapes and structures, right? If you were to take a look at that kind of system and actually take slow motion of it over a long period of time, some of the structures you might see in your toilet bowl in the water might actually be very similar to some of the things we see in our own Milky Way galaxy today. That's really because the laws of physics are showing themselves in the same areas, the conservation of angular momentum and those kinds of other spiral density wave functions on huge scales as well as on small scales. Now, let's look a little bit closer at what the Milky Way galaxy looks like, closer from where we are. You can pick up this poster from the New Scientist magazine. I think they downloaded these things. I've tried to use as many public available things as possible so you all can go and explore these later on your own. And you can see that this is a view from us. All this stuff back here is blank. Why? Because of the interstellar dust between us and that space. We literally don't know much about it. We can't see through all that dust. We use infrared telescopes. That helps a lot. But even they only get us so far. So a whole bunch of the Milky Way galaxy is just there, we think, based on our best guesses on how physics works, even if we can't see that particular area. Zooming in this space over here, here's the solar system you are here. That seems awfully small, doesn't it? So I'm going to click on it a little bit. Okay. Solar system, you are here. Remember, this is now 25,000 light years away from the center of the Milky Way galaxy. And look at all our favorite things, right? The North Star, Polaris, it's just right there. That's not very far, is it? Let me zoom back out again. See, big, huge galaxy. We think the North Star, oh, it's far away. It's a big thing. Nope, it's right there. Very, very close. And so all these other things that we look at, the Pleiades over here, okay, a few hundred light years away, about 420 if I remember correctly. That's a cluster, the Seven Sisters, as you know. And then if we look away from the center, the Horsehead Nebula, in this direction, of course, is the famous Orion Nebula, right? The constellation Orion is actually away from the center of the Milky Way as opposed to toward it. So that's ironically and happily why we can actually see it here in the Northern Hemisphere, because in the Southern Hemisphere, the Southern Hemisphere of Earth faces more toward the center of the galaxy than we do. So the folks in the Southern Hemisphere get a much better view. That's where you can see the Milky Way galaxy center in the direction of the constellation Sagittarius. Sagittarius A star is the name of the Milky Way black hole, right there. You can barely see it in the summertime here on Earth if you're in like Florida or Texas or Arizona. But here in New York and certainly in Seattle, we are out of luck. But that's okay. We still have other cool things to look at. And in the meantime, you can see all these other things, Cat's Eye, the Twin Jet. Some of you who are avid photography people, I heard Aaron talking to you earlier. This is roughly where all those other things are, right? And then here's Eta Carina, probably the most energetic star in the Milky Way galaxy that we can see with our eyes. It's not obscured by too much dust. But if you ever get to go to the Southern Hemisphere, or if you've ever had a chance to do astrophotography in the Southern Hemisphere, the Jewel Box, Eta Carina, some of the other clusters of stars in the area, just amazingly beautiful. And I encourage you to all take a look. So here we are, still not seeing most of this. But I will tell you a couple of things that are really neat. The Gaia data releases. Gaia is a spacecraft. Gaia used to be an acronym, GAIA, something about interferometric, astrometric something, experiment or something. And they just gave up. Eventually they just said, you know what? The Europeans, as opposed to NASA, who still has everything pretty much using acronyms, the Europeans said, we're just going to call this thing Gaia, okay? And that's what the name is. And they have taken, using this spacecraft, very careful data and measurements of the stars in the Milky Way galaxy that we can see so far. Okay, and it's taken years. The first data release was September of 2016, and then 2018. Notice how it went from this sort of stripy structure to this nearly absolutely perfect data release 2. That's because they got the positions, the colors, the brightnesses of more than 1 billion stars in our Milky Way galaxy. An amazing feat, tremendous. It's almost like this looks like an artist's rendition, doesn't it? But it's actually truly a photograph. And those individual stars are so close together, and the gas blobs are so real that you just simply are amazed at how beautiful it is. The early data release 3, you see these extra tracks. What's happened is that now that they've had the basic billion stars, they've looked at certain other objects with great care to see where they're moving, how they're going. And you see all kinds of other objects now, perhaps asteroids, perhaps exoplanetary systems, hard to say, but they just looked very, very carefully. And this was just released 2 months ago. And so this is available to the general public. If you want to see how those individual stars work, I encourage you to come take a look at this. And it's so much fun to just poke around, really. To go to the European Space Agency, cosmos.esa.imt, and if you go to Web Gaia, or just type into Bing your Gaia, or DuckDuckGo, or wherever you want to do it, then you can see that. Now, so in the last couple of minutes before I jump straight to the question, I believe all of them are in the Orion Spur, but not necessarily. This is a movie put together, imagined by what would happen when the Milky Way and the Andromeda galaxy collide. This is scientifically as accurate as possible at this point. And I'm running it without sound just so you can see what it would look like. Now, see, we're zooming out. This was put together by a number of my friends and colleagues who are really, really good at both numerical simulations and visualizations. So you see Triangulum M33, a small disk galaxy, and then Andromeda, which is a larger disk galaxy. This is the one that Edwin Hubble used to show that we are not alone in our galaxy island universe sort of existence. And watch what happens. This is 4, we think, billion years after now. So 4 billion years from now, there will be this massive collision, because Andromeda and the Milky Way are coming toward each other. And slowly, over a billion and a half years, while M33 kind of continues to dance around the outside, the Milky Way galaxy and Andromeda comes together to form one single huge elliptical kind of galaxy. It still has streaks coming this way and that way, and it's still moving in the center, but it takes 2, 3, almost 4 more billion years before it settles down into a single amazing object. So 4 billion years from now, I don't think we need to see that. 4 billion years from now, we're going to have some issues, but that's okay. I'm not going to change my retirement plans before then. It will still be lovely. For the longer version and description of that activity, I encourage you to come to this website, PBS Spacetime. If you haven't been there before, it's great. one of the hosts of PBS Spacetime, which is basically just sort of a PBS produced podcast about 10 minutes at a time. One of the hosts is.
See that bright object in the sky?
Oh no!
That's
Stop!
Andromeda,
Stop!
the closest major
Oh no!
galaxy to our Milky Way, and the most distant thing you can see.
Well, this is
within the
true,
galaxy.
but I don't want to
And
hear it.
it's
Stop! Stop! Thank you.
racing towards us at
What?
the rate of 110
All right.
kilometers per second.
I'm going to close you.
Eventually,
Close. Thank you. That's my way of saying that it's 8 o'clock, so I should wrap up soon. Come to this, the Andromeda Milky Way episode. Okay, season 4, episode 17. But the person who narrates, the host of this PBS Spacetime podcast, is named Matthew O'Dowd. Matt is one of my colleagues at the City University of New York. He's at Lehman College in the CUNY system. I'm at Staten Island, as you know. And it is a beautiful description and a walkthrough of that simulation of what's going to happen to us 4 billion years from now, and then 4 billion years after that. And then I will close with this object here. If any of you have never gone to cas.sdss.org, I encourage you to do so. This is actually a tool which the Sloan Digital Sky Survey people have allowed anybody in the world to look at cutting edge astronomical data. And this galaxy here, you see this? Notice it looks kind of like a backwards comma. And if you think back to just a minute or two ago, this galaxy kind of looks like what the Milky Way and Andromeda looked like about 1 billion years after they first collided. Remember, at the end of that video, which I closed just now so we wouldn't have to hear it, so I can't show it to you, I'm sorry. But at the end of that video, it was kind of an elliptical shape, right? Well, 1 billion years into the collision, it's elliptical, but it's still got this little extra structure, and it's got this sort of comma coming down this way. This is an object which I have been joyously studying for the past couple of decades, since it was first accidentally discovered in 1991. It turns out that if you look at it carefully, its central region has these 2 spikes, the nitrogen 2 spikes, which indicate clearly, at least to me, that there is a supermassive black hole in the center that is slowly sputtering out. It's low ionization, but it's there. Meanwhile, these very deep absorption lines here of hydrogen, okay, so it's called H beta, H gamma, H delta, etc. They're so deep and so strange that they confused the Milky Way galaxy, well, the galaxy identification program that the Sloan Digital Sky Survey thinks. It thinks that this object, because of this shape, is actually a galaxy that's about 4 billion light years away from Earth. It's not. It's only about 1.5 only. But what it does is this is a galaxy whose stars have been burning fiercely until 1 billion years ago. A huge burst of star formation happened. There was a collision, and now the stars have stopped forming. These are all the fossilized population of galaxy stars that are about 1 billion or so years old, with a little old black hole in the center slowly sputtering as it runs out of stuff to eat. So it is a way of studying the overall aging process of the universe. This is part of my research that I'm doing now to try to understand it. So what I will end with is the title of this talk, right? I called it Long Live the Milky Way Galaxy, because of course it will live long for about 4 more billion years, but then it's gonna be smushy and we might be a little sad, but actually I'm not sad, because then it'll become like this wonderful galaxy that I've been studying for so long, and all these other galaxies as the universe changes as part of that whole process of cosmic discovery and our aging. So slowly but surely, we are learning a little bit about that ocean that we live in as we go around in our little goldfish bowl. So long live the Milky Way, and I hope you all have a great time. Thank you again for giving me the opportunity to share some cool stuff that I really like about the universe. And I'm happy to answer some of the questions. I believe one of you is going to read some questions for me or help me out with that.
Yeah, absolutely. Well, firstly, thank you so much for the absolutely fascinating walkthrough. That's just incredibly cool. We had a couple questions on the last section in particular. I want to make sure we we get to. So in that collision situation, M33 was also in that picture. Why does M33 avoid capture, avoid the collision?
Ah, that's a great question. M33 is a dwarf spiral. It's one of the few spiral galaxies that we know of that has strong spiral structure, but no supermassive black hole in the middle that we can detect. The fact that that thing has survived for so long near Andromeda suggests that its orbit is very stable and quite far away from the gravitational tidal effects of Andromeda. So my guess, since I didn't perform the simulation, as to why M33 survives is that it just stays far enough away. In the same way that if you don't fall into a black hole, it's not going to suck you in unnecessarily. That's my best guess. As I watch it, I do notice that it seems to get a little truncated around the edges. So it's possible that some of its outer portions do feel that kind of tug and pull. So you want to be careful to see what that is. One day I'll probably go ask, Frank Summers, Roland Mondeville, some of those folks who created that simulation. Gertina Bessler at Yale, she has been doing some amazing work about dwarf galaxies around larger galaxies. So that's probably the definitive word on that. Great question.
Got it. Thank you very much. On a similar note, are all the elliptical galaxies we see the results of mergers, or are there other ways that kind of structure would be able to form?
The latest simulations that have been done about structure formation in the universe, starting from just a few 100 million years after the Big Bang to the present day, suggests that there are no large elliptical galaxies that have formed without things merging into them. If they're a small dwarf galaxy, it's possible that, like M33 in this simulation, that they've escaped being torn apart or subsumed into other galaxies over an entire 13.5 billion year period of time. But anything large, anything about as massive or more massive than the Milky Way galaxy that's elliptical shaped, probably could not have achieved its ellipsoidal shape today without substantial collisions, either big ones with galaxies of similar mass and size, or hundreds or even thousands of little tiny ones that have sort of been smacking it every once in a while over billions of years. It's a great question.
So one that I had it was more a private one, but so when two galaxies collide, obviously galaxies are mostly empty space. So except for those very small number of stars that may directly collide, or features that may directly collide, what would be sort of from our neck of the woods, what might be the experience of that kind of collision? Would our sun be impacted? Would our star collapse?
What a great question, and it also dovetails with the question that I see in the chat from Ben Waldman. Let me just give a shout out to Ben, because Ben and I went to college together. We sang in the Glee Club together. So Ben, it's great to see you. Hello, thank you, wonderful question. And let me give you the answer. Because we don't know exactly the matter distribution in our galaxies, whether in detail, as you said, about the empty space between stars and stellar systems, or the huge dark matter halos that surround all of our galaxies, it's very hard to know if we got it right. We have some good guesses. We think we got it right. But again, just like Edwin Hubble got the measurements wrong earlier because Henrietta Swan Leavitt was also not quite bang on, that is stuff that is yet to be decided. That said, we're pretty sure that even though we are not likely to hit anything in direct contact, a gravitational interaction, even from billions of miles away, is more than enough to cause permanent changes to a solar system. So remember that we're talking about systems that go on, this collision goes on for billions of years, right? Even say things that we feel are permanent in our own solar system, something like Saturn's rings. Saturn's ring system cannot be older than about 100 million years. which is less than 1/30th or 1/40th of the length of that collision video. It's just these things happen and slowly they change. As these other stars are whizzing by us and missing us, but changing things, they're going to change the orbits of the planets, orbits of the dwarf planets or any comets and so forth. There's going to be all kinds of changes. So we probably will see quite a light show from a distance, but at the same time, our stable, cheerful existence within our solar system will probably be highly disrupted. Fortunately, I have great hopes that 4 billion years from now, our technology, if we as a species survive, will allow us to just shrug off this collision as if it were a fascinating fireworks display lasting 4 billion years, rather than something that would end life on Earth as we know it, which it very well might if we don't do anything about it. Great question.
And then we'll just do one more, and then I think we'll be right at the top of our time. And thank you. There's a couple questions we didn't get to, and we'll try and answer those in the chat. Thank you all. But last one here. Of all the galaxies we observe, what percentage or what share do we think may be in the process of merging or colliding?
Oh, great question. When I started graduate school, the percentage appeared to be something like 5. About 1 out of every 20 galaxies seemed to be within sort of the half billion year or billion year window of a collision going on at the time. But now, as we have better and better data, we are able to detect whether or not some of these collisions are going on with smaller bodies. For example, is something the size of the Magellanic Clouds crashing into something the size of the Milky Way? And from that, we may not see a huge distortion in the shape of the galaxies from our vision, but we can see the stars having different velocity profiles. We can see warps in the disks. We can see streams of stars in strange ways. So the answer is that although probably a few percent of galaxies today have huge collisions, it could be as many as half of all galaxies our size are undergoing some sort of collision or another. So the universe is a pretty dynamic place, and we have a pretty lucky spot where we're watching to see all this cool stuff happen.
That's that's more than I would have guessed.
Yeah, more than any of us guessed, really. It's quite amazing.
That's incredible. Well, thank you so much, Charles. That's just a fascinating conversation, and thank you, everyone. And I will pass it back over to Dwayne for our next segment.
Thank you, Kyle. Before we keep going, I have a fun fact about the band Warren Dunes. Did you know this band, they got their unique name from the Warren Dunes State Park in Southwest Michigan. I don't know how many people that are on this call are either from Michigan or are familiar with that area, but yeah, there you go. The name came very easily to the band. According to musician Dominic, he said, Warren Dunes is the place where we first really experience wonder and raw inspiration. With that said, please welcome back to the Zoom stage, Warren Dunes.
Thank you so much, Dwayne. That was wonderful. And thank you so much to Charles for that fascinating discussion. I appreciate how when things that seem very mystifying become demystified and then create even more mystification. And I appreciate that so much about astrophysics, and it's nice to hear somebody bridge that gap for me so I understand it a bit more, and I'm filled with wonder once again. So thank you all for being here. I want to give a shout out to Eva Walker of the Black Tones in KEXP. I think she's tuning in, and she's a space lover as well. So we're going to play a song for her and all of you. It's called Fishbowl. 5, 6, 7, 8.
Under
Thank you all so much. This is really a privilege to be here with you. What a treat. And just to give you a little bit of insight into our family band and our connection with all things space, Jared is my partner. This is his brother, Dom, my brother-in-law. And we both have a son. And when we were trying to figure out who we wanted to name him after, we had been watching the original Cosmos at the time. And so one day, I remember I woke up and I said, you know who we really admire a lot? Is Carl Sagan. So we got a little kid named Carl, and he's upstairs entertaining himself while we're down here. So I just wanted to shout Carl out. He also loves space. So anyhow, this next tune is called No Mud, No Lotus. Hope you enjoy it. 5, 6, 7, 8. Reaching out to catch bit.
All right. Yes. All right. How about that? I don't know about you, but I can't perform with two keyboards at the same time. And shout out to Dom in the back there, way in the back. He exists. Yes, he's in the band. All right. Well, thank you so much, y'all. Yeah, and just a reminder, everybody, we have a couple more segments left. We're just getting started, so this is great. I'm glad everyone could be here. We're gonna have a lot of fun and ways to connect at the very end. We'll have some reminders, but let me turn it over to Christina.
Thanks. We'd like to go ahead and welcome Dr. Melissa Rice, an associate professor of planetary science at Western Washington University, who holds a joint appointment in both the geology and physics and astronomy departments. She received her PhD from the Department of Astronomy at Cornell and was a NASA Astrobiology Institute postdoc fellow at Caltech from 2012 to 2014. Her research is Mars focused, and she is a collaborator on the active Mars exploration rover opportunity missions, as well as a participating scientist on the Mars Science Laboratory rover mission, among other projects. She also leads the Western Mars Lab, which is the planetary geology research group at Western Washington, comprised of undergrad and graduate students in various fields. The lab's primary research focus is deciphering the history of water on Mars. The group works directly with two of NASA's Mars rover missions, the Curiosity rover, which is currently on Mars, and the Perseverance rover, soon to be landing on Mars, hopefully uneventfully, on February 18th of this year. They also assist NASA in testing instrumentation, operating the Mars rovers, and performing data analysis. If you'd like to support the lab's ongoing commitment to space or exploration and research, you can donate to the program by clicking on the link we will provide in the chat window. Any funds given will go toward updating the Mars Rover Operations Lab and providing opportunities to as many student researchers as possible. And on a side note, I asked her earlier today what her favorite planet was because I assumed it was Mars, but she said no, it was Earth, but that she does have a never-ending dislike of Mercury. I'm not sure what the personal story is behind that, but Dr. Rice, the floor is yours.
Thank you so much. And thanks so much for having me. This is perfect timing to come and speak to you about Mars exploration and the Perseverance mission, because as we heard, the mission is on its way to Mars and is preparing to land on February 18th. That is next Thursday. For those of us in the Seattle area on the West Coast, that's going to be 12:55 p.m. Pacific time. Tune in. NASA's going to have great coverage. The Planetary Society will have commentary as well. Lots of places to watch. So make sure to be watching there. And then hopefully what I'm about to show you is just going to get you even more excited so that you can't sleep at all between now and next Thursday. I certainly know I won't be able to. I have some slides to share here. So let me put those in the center here, and these will just aid the story that I'm about to tell about the Perseverance rover and what it is planning to do once it gets to Mars next week. I love saying that, next week. This is an astronomy group, so I thought I would start out with the night sky and how Mars has appeared to the human mind and the human eye over most of our history, which is that bright dot of red light, often the brightest thing that we see in the night sky, very recognizable, solid, steady, bright red light. And even 100 years ago, we didn't have a very good sense of what Mars was all about. 100 years ago, this was the best astronomical image that we had ever taken of Mars. And you can start to see.
Some Mars. Let me write it down.
Sounds like someone needs to mute. What you can see in this first real astronomical image of Mars from the Mount Wilson Observatory is that you can start to tease out that Mars is more than just that bright dot of light in the sky. Mars was in its very first steps of becoming a world, not just an astronomical object. So you can see here that there are some dark areas, there are some bright areas, there are what looks to be a little hat on the top of Mars. Those are the polar caps of carbon dioxide ice, which we know now. But in the past 100 years, Mars has really come into focus, both with improvements in ground-based telescopes, space telescopes like Hubble, and now our fleet of orbiters and landed spacecraft crawling around on the surface. And so right now, we not only have this spectacular view of Mars as a dynamic world today, but through our robotic geologist explorers on the surface of Mars, we have a very good idea of what Mars might have been like in its ancient history as well. And our rovers are really geologists. They read the rocks like pages in a book. And what they're telling us about Mars's ancient history is that Mars was once a world that would have been much more familiar to all of us, a world with precipitation, with weather, with rivers, with lakes, and maybe even large bodies of water like an ocean. And so this is the picture of Mars that is emerging from our exploration of the ancient rocks on the surface, that at one point in its history, Mars was a more Earth-like place. And then that leads us to the big question. If Mars had water, if Mars was much more like the Earth at some point in its ancient history, could there have been a second genesis of life? Could whatever magic spark that led to the emergence and the diversification of life here on the early Earth, could that have happened on early Mars when early Mars had the very similar conditions to those on the Earth? So that's the big question that we're after with Mars exploration. And these are the tools that I get to use to try and answer that question. This is NASA's Rover family portrait. All of the rovers that have been to Mars lined up on the front steps of the Jet Propulsion Laboratory. And in the middle, some of you may remember the Sojourner rover from the 1990s that went with the Pathfinder spacecraft. On the left, Spirit and Opportunity, two twin robots that went to Mars in 2004. And on the right is the big beefy Curiosity rover, went to Mars in 2012 and is still exploring the surface of Mars today. I spend a good part of every week helping to operate the Curiosity rover on Mars and to help the team decide where the rover should drive, what it should photograph, which rocks it should investigate next. So Curiosity is still very much alive. But we have someone new going to Mars, and you might expect that since each of these rovers has gotten bigger and beefier and more complicated, that the logical next step in NASA's robotic Mars exploration might be something like this. In reality, Curiosity's form worked so well that NASA decided to essentially build something that looks like another Curiosity. However, the next rover, Perseverance, it's going to look like Curiosity, but it has a much different mission with much bigger and much more ambitious goals. And we'll talk about that in a minute. So yes, Perseverance looks a lot like its predecessor. This rover, which launched in 2020, looks a lot like the one that launched in 2011, but we have a decade of new technology, and so some cool tools that this rover has, and an entirely different goal, which is a much more direct search for evidence of ancient life on Mars. So this mission is on its way. I wish we were here in person so I could take a show of hands and let you all applaud for those who got to watch Perseverance's launch on July 30th of last summer. I had planned to bring about 10 students to Florida with me to watch the launch and a film crew from Western Washington University, but we wound up all watching from our living rooms. And similarly, we were all planning to descend upon the Jet Propulsion Laboratory next week to be there together with all of the scientists and engineers when Perseverance lands, but we will be doing that distributed from our living rooms again due to the ongoing pandemic. But we're finding cool ways as a team to still connect, to have that camaraderie together, even though we're working so physically spread out around the country and around the world. So Perseverance has been on its way for quite a while now. And what's going to happen next Thursday is what you may have heard of as the 7 minutes of terror. So after more than 7 months of traveling, about 100 million miles between the Earth and Mars, Perseverance is only going to take 7 minutes to get down to the ground after it reaches the top of Mars's atmosphere. Now, we call this the 7 minutes of terror because a series of things have to happen exactly right and exactly in the right order in order to get that rover from its speed at the top of Mars's atmosphere, about 13,000 miles per hour, down to its speed when it hits the surface, which we hope is not 13,000 miles an hour, but something more like 1 to 2 miles an hour for a soft touchdown on the surface. Okay, so the first thing that has to happen in those 7 minutes of terror is a supersonic parachute has to deploy. This is a parachute that has it has a diameter about the size of your living room, maybe a little bigger. This is the largest parachute ever sent to another planet, and it can slow the rover down as it descends through Mars's atmosphere. But Mars's atmosphere is very thin. It's about 100 times the atmospheric density of the Earth's. And so even a supersonic, ginormous parachute can only slow this spacecraft down to about 900 miles an hour. There's still a lot of slowing down that has to happen in the rest of those 7 minutes before the rover gets to the surface. And this is where the jetpack comes in. So the rover is going to separate from its back shell that has the parachute attached, and it's going to go the rest of the way on thrusters. So this is a jetpack that has a very smart new landing technology built into it. It's called Terrain Relative Navigation, or TRN. And what this is going to do is take pictures of the surface constantly as the jetpack is lowering the rover down to the surface. And it's going to be comparing those pictures that it's taking of the surface of Mars as it's landing. It's going to compare those to a map that we've loaded onto the spacecraft's computer. And so it's going to be doing real-time comparisons to this map. And the map that we've loaded has all of these red areas of places where there are hazards, a big cliff, a big sand dune, a boulder field. And so the rover knows which spots on the surface are dangerous. And as it's landing, it's going to be assessing the terrain right in front of it and using those thrusters in the jetpack to navigate away from the spots that it knows are hazards. So what this means is that we can very smartly navigate as the rover is landing down to a specific location that we know is safe and a specific location where the really juicy science is going to be. More on that in a minute. So that jetpack is going to lower the rover almost all the way down to the surface, but not quite all the way. It's going to lower down to a few meters above the surface, and then it's going to hover. And the rover itself is going to lower beneath the jetpack on a series of tethers. This is called the sky crane maneuver. And those tethers are going to be what takes the rover all the way down to the surface, and its wheels are going to deploy like landing gear. And the rover is going to land on those 6 wheels, the same 6 wheels that we're going to depend on to drive everywhere we want to go on Mars. So we really hope that this is a soft landing and not what NASA calls a hard landing, which is a euphemism for a crash. So fingers crossed that every step works. And then there's one more thing that has to happen. That jetpack, if those tethers don't detach, it's going to be on a collision course with the rover. So those tethers have to get cut, and the jetpack is supposed to fly away and crash somewhere onto the surface. Now, at this point, the rover is going to be transmitting its data back to Earth and telling us exactly how the landing went, exactly where it landed. That's going to be one of the first things that us on the science team are going to be scrutinizing, are those latitude, longitude coordinates, so that we can put a pin on our map to see exactly where Perseverance is, and then use that location to start planning out the full scope of the mission. Perseverance is going to be communicating to us through the deep space network. This is a series of large radio receivers around the world. We can communicate with Perseverance at any time, but for the most part, we are only going to be talking to Perseverance a couple of times a day. That's because Perseverance has, while it does have a high gain antenna that it can transmit signals directly to Earth with, we can get much larger bandwidth if we communicate through the network of satellites, of orbiters that NASA and the European Space Agency have in orbit around Mars. So Perseverance is going to be communicating using a relay communication system of Mars's satellite networks back to the Earth. And so these satellites, they'll be visible to Perseverance in the Martian sky a couple of times a day. And so that's when we'll receive the downlinks. And when Perseverance transmits its last bunch of data for the day, the rover is going to spend its nights sleeping. The Perseverance does have its own power. It has a radioisotopic power source, plutonium-238, that's constantly generating heat, which we turn into electricity to charge the batteries. But Mars's nights are so cold that we can't really do much with that power over the course of the Martian night, other than sit and charge our batteries. So Perseverance is mostly going to be sleeping at night. And when Perseverance sends its last transmission of the day and then goes to sleep at night, that's when we, the scientists, the engineers who are going to be operating Perseverance, that's when we wake up and receive that data and make the plan for what Perseverance will do the next day. So we're going to be working on the Martian night shift once Perseverance lands. And it's not just like working the night shift, it's working the Martian night shift, which means that our schedule is going to shift with the schedule of Mars's schedule. Okay, so Mars's day is very similar to an Earth day. It's 24 hours and 40 minutes. That sounds pretty close to an Earth day in the scheme of things, but that 40 minutes is just different enough to get really annoying. So let me just give you an idea here. Okay, here's a sense for Earth and Mars and their orbits. And the reason why we don't communicate constantly in real time with Perseverance is because of that relay lag of anywhere between 5 and 20 minutes, depending on the orientations of Earth and Mars and their orbits. So we can't control Perseverance with a joystick. We have to send a load of commands to Perseverance and then wait for it to execute those commands and send it back. Okay, so I told you that Mars's day is just different enough from Earth's day to be annoying. And to give you a sense of what that's going to mean for myself and my colleagues who are operating this rover for the first part of its mission, I took a screenshot of what my calendar is going to look like in the first week of March. And I've put my sleep times in here because I have to schedule my sleep times or else I'll forget to go to sleep. And look at how this day is going to shift forward by an average of 40 minutes each day. And I'll be waking up with just a couple of hours to get ready and get my breakfast before that first downlink comes from Perseverance, before Perseverance goes to sleep in its night. And my days are going to be starting in the middle of the night. And I am going to be cycling my work schedule through the Earth clock a full 3 rotations over the course of 90 days. Now, NASA only makes us work this schedule for 90 days because sleep scientists have studied the teams working on previous Mars missions and determined that after about 3 months, we're all behaving as if we're legally drunk because we're so tired and jet lagged. The other thing is that marriages start to fall apart after 90 days of 2 people in the same household living on this schedule. Throw some kids in the mix who have a normal Earth Day school schedule, and it becomes really tough. So I am grateful that this is going to be a short-lived process, but it's going to be interesting for sure. Okay, so that's what's happening leading up to Perseverance's landing next week. And let's talk a little bit about where Perseverance is going, because this is a really exciting landing site. And that new landing technology, the terrain relative navigation, has opened up new swaths of Mars that were previously too hazardous for our rovers to go. We can now really narrow in on a safe spot to land next to some of these most scientifically spectacular sites on Mars. So NASA went through a 5-year landing site selection process. And in 2018, just 2 years before the mission launched, the scientists selected a landing site based on a series of scientific criteria after the engineers had already narrowed down a bunch of sites because of this specific engineering criteria. We couldn't go to a place that was too high in elevation because there wouldn't be enough atmosphere to slow down that parachute. We couldn't go to a place where the winds were too high because as that rover was landing, the winds might have chaotically blown the rover someplace else. We couldn't go to a place that had too many sand dunes, that was too cold during the Martian winters. So all these criteria. And in 2018, we had narrowed all of Mars down to 3 specific sites, and we selected Jezero Crater as the winner. Jezero Crater is a spectacular site because it's really old. The rocks within the crater are estimated to be 3.6 billion years old. That's billion with a B. We have very few sites on the planet Earth that preserve sedimentary rocks that are 3.6 billion years old. So we're going to go to a place in the solar system that better preserves this early period in the solar system's history. And these aren't just any sedimentary rocks that are preserved in Jezero Crater. These are rocks in a river delta. So the shape of that feature in this image with that purple color looks kind of like the Mississippi Delta, a fan-shaped series of rocks with channels over it. This was the spot where a river had been bringing water and sediment and maybe organic molecules into an enormous crater lake. And where that sediment hits the standing body of water of that lake, there's an energy difference and the sediment gets deposited right then and there, right where the river meets the lake. And that's what this river delta is. And as those sediments are deposited in this lake, they trap any living microorganisms that might have been present in the lake and that might have been carried through that river in the sediment. We know from places like the Mississippi River Delta, from other delta deposits on the Earth, that these rocks are a fantastic way to preserve evidence of life from many, many millions of years ago. And on Mars, we're hoping that this preserves evidence of ancient Mars life from possibly 3.6 billion years ago. Now, that's the big question that we're after. Did Mars ever have life? And if it did, was it present in that lake in Jezero Crater? And if it was, is evidence of that life preserved in those delta rocks? That's the big question. Now, how are we going to answer this question with this robot operating far away? Really, the best thing that we can do is not use Perseverance to answer that question, but to use Perseverance to find the rocks that are going to have the best possibility of answering that question. And then to collect those rocks and eventually bring those rocks back here to Earth. That's the ultimate goal, to get the rocks with the best potential for preserving Mars life back here on Earth. And it's such a big question, the question of life on another planet, that we really have to throw our whole scientific arsenal at it. We can't answer such a big question with high confidence with a rover on Mars. We really need to get those rocks here on Earth so we can use the most up-to-date technology. We can use instrumentation that sometimes fills up an entire room. We need big instrumentation, and we need to be able to look at the same rock samples in multiple laboratories in order to verify that the results that we get are reproducible with multiple instruments. So getting rocks back to Earth is the ultimate goal here, and it has been for a long time. But it's a really hard thing to do because you have to launch off of Mars. And we have never launched anything off of Mars. All of our rovers previously have gone to Mars to live on Mars and die on Mars. And someday there'll be a Smithsonian museum on Mars, and the Opportunity rover will have a velvet rope around it, and we'll all be able to go and see it in place where it died. But we're never getting it back to Earth. So to get these rocks back to Earth is a big endeavor, and there's a reason we haven't tried it yet. We really need to get these rocks into Earth laboratories so that we can get measurements like scanning electron, microscope images, like mass spectroscopy data of isotopic evidence that we just can't do well enough with a miniaturized instrument on board a rover on another planet. So we've got to get those to Earth so that we can look for things like these microfossils, and also very, very teeny tiny isotopic differences with high precision to see if there's any evidence for life, what we call a biosignature, a signature of ancient life. So we've got to get those rocks back to the Earth. And the way that we're going to do that is collect what we call a sample cache, a collection of a well-curated collection of rocks from the surface of Mars that are going to help us answer these questions. And we're going to do this in 3 steps. Perseverance is the first step. It is the sample caching rover. It's going to use its sophisticated set of instruments to identify which rocks are the juiciest, which ones are the ripest for the picking. And we're going to drill into those rocks with the rover's arm, extract core samples, put those core samples into fancy sample tubes, hermetically seal them, and then leave them on the surface of Mars. Step 2 is called the fetching rover. This is a follow-up mission that is going to be a joint venture between NASA and the European Space Agency, where efforts are underway, and the plan is for this mission to arrive at Mars in the year 2027. This fetch rover is going to pick up the sample cache that Perseverance has collected and left behind, and it's going to drive it to a launch vehicle that it will have brought with it. Now, it takes a lot of fuel to get all the way from Mars back to Earth, so we're not going to attempt that in a single go. The fetch rover is going to bring those samples to a Mars ascent vehicle that'll launch the samples into orbit around Mars. But those rocks are just going to stay in orbit around Mars until the 3rd mission comes and grabs those rocks from orbit around Mars and then brings them all the way back to Earth. So this is a big venture. It's going to be probably more than a decade until we get the rocks that Perseverance collects back into labs on Earth. And who knows what technologies we'll have? Who knows what advances there will be in scientific instrumentation here on Earth by that point? And that's a big reason why we got to get those rocks back here, because our technology is advancing so fast that all of the instruments that are on board Perseverance are already almost 10 years out of date. So we've got to get those rocks here so that we can catch up with our technology. So Perseverance is a sample caching rover. And in order to select these rocks and put them in this very specific, controlled, hermetically sealed caching system, Perseverance needs an entirely new set of instruments and a brand new sample caching system. Perseverance has a couple other upgrades from Curiosity that I want to point out, one of which I think is something you might not have thought about. But the wheels have changed subtly, but very importantly. Perseverance is that Curiosity's wheels which had this nice kind of zigzag pattern and were thinner and wider and lighter weight, they got punctured by the rocks on Mars. Every time we send a new rover to Mars, we are learning so much about the geology and the scientific history of Mars, but we're also learning about just what Mars is like as an environment and how to navigate on Mars. And it turns out that the rocks at Curiosity's landing site were super sharp and super pointy, and they just shredded through Curiosity's wheels. So we're beefing those up on Perseverance based on what we've learned before. Perseverance is also carrying a sidekick. This is a helicopter called Ingenuity. This is a technology demonstration. The first time a powered craft will ever have flown in the atmosphere of another planet. This is a big deal. This is a Wright brothers moment on Mars. And this helicopter has to be super small. It's about the size of a softball or maybe a large apple. And it's super lightweight. It weighs about 1 kilogram. And its wingspan is 4 feet tips to tip. It has 2 blades. And it has to be super small and super lightweight with big wings to get any lift at all in Mars's thin atmosphere. Mars's atmosphere, again, is 100 times thinner than the Earth's atmosphere. So I'm really excited about this helicopter because it also has 2 cameras on board. And it's going to be taking pictures of Perseverance as it's flying around, which will be really cool to see our rover from that aerial perspective. And it's also going to be taking pictures of the terrain ahead of Perseverance. So we can use those photos from above to see up and over obstacles in the landscape and to help us plan for the traverse of where Perseverance will go next. So Perseverance itself has 23 cameras. The whole mission has 25 because there are 2 on that helicopter, but 23 cameras. This is more eyes on board than we've ever sent to another planet. I've started thinking of Perseverance almost as a fly with all of those eyes. It's going to be looking in all directions, but there are 2 cameras which are near and dear to my heart. And these are the Mastcam Z cameras, the ones that look like 2 eyes on the top of the rover's head. This is an instrument that I've been involved with from the beginning. Back when NASA announced that they would be sending a follow-up mission from Curiosity, they announced that in 2013, and they put out a call to the entire world to propose what scientific instruments should be built to fly on board the Perseverance rover. And I was part of a team that came together to propose a specific set of cameras that would be like Curiosity's cameras, which are called the Mastcams, but that would also have an improvement, which is the ability to zoom way in to distant features on the horizon and Mars's landscapes. And so we proposed an instrument, Mastcam Z. The Z stands for zoom. The first time we'll have zoom lenses on the surface of another planet. And maybe that doesn't sound like such a big deal. Maybe, you know, you've had a zoom lens on it for your camera forever now. It's a big deal for Mars because at any time you put a moving part onto a spacecraft, that moving part is something that can fail. That moving part is something that a grain of dust can get into and clog. So every new point of failure is a big risk for the mission. So just having those optics, being able to zoom in and out was a big step up and a big complication in developing these cameras. So Perseverance is going to have these Mastcam Z cameras, which are really going to be the scientific eyes. Not only will they be able to zoom way in and out, but they'll be able to see in full color, human-like color. They'll also be able to see in colors that have been very precisely optimized to bring out the color diversity on Mars. Now, in most pictures that you've seen from Mars, everything looks like some shade of orangish, reddish brown, right? Mars is called the red planet for a reason. But if we had evolved on Mars, our eyes would be able to see the full colors of the Martian rainbow. Our eyes would be especially tuned to the subtle differences in all of those shades of orangish, brownish red. And so that's how we've designed Mastcam Z, to be specifically tuned to the color differences of Mars. And the reason why I'm harping on this is because that has been my specific role and what my students at Western Washington University and I have been working on for Mastcam-Z is those specific color selections for Mastcam-Z. And the way that Mastcam-Z is going to see in color is we've chosen 16 specific color filters that are going to be in front of the camera's CCD detector. And these filters allow specific wavelengths of light with a specific bandpass that we've selected to pass through. And we have 2 Mastcam-Z eyes, 2 cameras, each with a filter wheel with 8 filter positions, one of which is clear. So we'll get approximate true color imaging with the Bayer filter that's bonded onto the CCD. This is the same kind of Bayer filter pattern that's in a typical SLR camera or your smartphone. But we also have this filter wheel in front of that. And so we can select different filters to let different wavelengths of light pass through. And these have been optimized to places in the infrared part of the spectrum, the near infrared, where there are absorptions in the spectrum due to iron oxides and due to the presence of water. So these eyes will be able to look directly for water that is locked in the mineral structures of these rocks on Mars. So that's what we've been doing with our research group up in Bellingham to contribute to the science of Mastcam-Z and Perseverance. And because of that contribution, we were also able to go and take pictures with the Mastcam-Z cameras before they were sent to NASA to be integrated onto the rover and then sent to Florida and put on the launch pad. So here we are. This is a group of students, grad students and undergraduates from Western Washington University. We're down at Malin Space Science Systems, which is where the Mastcam-Zs were built. And we're standing outside the clean room. And you can see inside there, connected to a bunch of cabling, pointing at a lab sphere, integrating sphere, are the Mastcam-Z cameras. And you can see 2 of the engineers in their bunny suits. They like to say they wore masks before it was cool. They're in there operating the Mastcam-Zs, and we came down to the control room to take pictures of calibration targets that are going to help us interpret the data that we get once Mastcam-Z goes to Mars. 3 of these students now, after this trip, got jobs working for Malin Space Science Systems. So they're down there every day now, and they're going to be the ones actually operating the cameras when they get to Mars next week. I got to show this picture because this is a real picture taken with Mastcam-Z. These are the same Mastcam-Z cameras that are now on Perseverance, on their way to Mars. And I like to think of this picture as a birth image. This is like the Mastcam-Zs being born and opening their eyes and seeing their parents for the first time. So these are all of the scientists and engineers who are on the team that designed the cameras. This is our science team, and some of these folks were in the clean room building the cameras as well. And I am in this picture twice, actually. I'm kind of this funny face through the mirror here. And the reason for that was when this photo was taken, I had to teach a class back at Western. So I had to fly home and go teach my class. But the team called me and said, hey, we're going to take the Mastcam-Z birth photo. Get on Skype and we'll hold you up to the mirror. So I got my image on here as well. And you can see a couple of my colleagues had gone home as well and are still got to be in the photo as others held up their laptop screens. So yeah, it just tickles me that the actual cameras that are going to be taking pictures on the surface of Mars next week captured a photo of all of us as well here on Earth. So let me tell you about something else that's really exciting coming up for Perseverance. We've talked a lot about Perseverance's big objective of collecting this curated sample cache that's eventually going to make its way back to Earth. Another big thing that Perseverance is going to do is pave the way for human exploration. And this is an actual objective of the mission, is to make progress, make real steps in the process of preparing for human exploration of Mars. And there's a super cool instrument that's on board the rover called MOXIE. And this is going to be a chemistry experiment where for the first time, we're going to take carbon dioxide, which is what 95% of Mars's atmosphere is, going to suck that carbon dioxide out of the air, and then separate the oxygen and convert it to breathable O2, molecular oxygen. And this is a proof of concept that, yes, we can take Mars's atmosphere and create breathable air from it, and that that molecular oxygen can also be used as rocket fuel. So someday I can imagine that before humans get to Mars, maybe a robotic spacecraft carrying an instrument like MOXIE will go to Mars ahead of time. And we'll start this process of converting Mars's air into breathable oxygen and rocket fuel. And then when the astronauts arrive, they've got their air canisters full and ready, and they've got a fuel tank full and ready for their return flight home. So NASA likes to say that MOXIE is going to breathe like a tree. It's going to inhale carbon dioxide and exhale oxygen that then we can breathe. I think this is super cool, and I can't wait to see MOXIE in action. Well, that's the last of my slideshow, and I hope we've got some time now for Q&A, because I am really excited to hear what you all want to know about Perseverance and the future of Mars exploration. So why don't I go ahead and stop sharing my screen and open it up for some questions.
Yeah, thank you so much, Dr. Rice. That was fantastic. I know I'm super excited about the landing and all of the wonderful science and things that Perseverance is going to teach us about Mars. And I know I've set my alarm and set some time aside at work to make sure I get to watch it as well. So I hope everybody gets that opportunity. We have plenty of questions for you here. A couple specifically about the Mastcam Z that you've been working on. So is it like looking at light at specific wavelengths? So we were just kind of curious about the choice of using a camera with a Bayer matrix instead of like a monochrome sensor. Could you talk a little more about that?
Yeah, the Bayer filter definitely makes the kind of multispectral filter imaging that we're going to do more complicated, because all the light that passes through a filter of a specific wavelength that we have chosen also has to pass through that Bayer filter pattern. Those red, green, and blue filters are bonded onto the CCD. So why even have that Bayer filter? And the reason is because our multispectral imaging, the imaging that we do with the various filter sets, that's only going to be used a fraction of the time. For the most part, I would say maybe 80% of the images that Mastcam Z is going to take are just going to be taken through a clear window in that filter wheel, just through the Bayer filter, so that we can get an approximate true color image. Most of the images that Mastcam Z takes will be helping the rover's navigation. We have two eyes with a stereo separation of about 30 centimeters that will allow us to get 3D terrain meshes and help us decide how to navigate through the landscape. For that type of imaging, we don't need all of our filter sets. We're only going to use those filters with the various wavelengths of light out into the near infrared when we really want to do a mineralogic investigation, when we really want to follow up on a picture we've first taken of the surface and then ask, well, what is this rock made of? Does this rock have oxidized iron in it? Does this rock have hydrated minerals in it? It's going to be the next step in our reconnaissance process. And if we see something interesting with our Mastcam Z filter set images, at that point, we might decide to drive the rover right up to that rock and reach out the arm and use the instruments that are on the end of the arm, like the Raman spectrometer or the X-ray fluorescence instrument. So it's a series of next steps in the investigation. And at the end of that series, the final step will be, let's drill into that rock and take a sample and put it in our cache to bring back to Earth.
Cool. The follow-up with that, had another question, excuse me, of how specifically are you going to keep that cache in the same situation, or the same environment as it was captured on Mars on its trip back to Earth and once it's here on Earth?
That is a great question. How are we going to ensure that it doesn't undergo some wild temperature swings, say, that might dehydrate the minerals that are in that rock, or might, how are we going to prevent it from something like UV exposure that might damage the organic molecules that are within that rock? Those are very good questions that the engineers are taking very seriously. And for Perseverance's part, we are going to put the samples in a controlled environment in their individual sample tubes, and those will be hermetically sealed. And when we leave them on Mars, we'll be sure that they are left in a spot that is not going to undergo wild temperature fluctuations. So we'll be measuring the atmospheric conditions on Mars. We'll be measuring very localized conditions and taking that into account when we drop off the samples into their depot. So for their journey back to Earth, that's when things are going to get really complicated, and that is in the process of being designed and developed right now. So all I can say is that those are big concerns that are being taken under consideration. And I don't know exactly how we're going to do it, but I have confidence that the engineers will figure out a way to control that environment for the full duration back. And we have done that before. You know, we have sample return missions to comets that have brought materials back. So we have some experience there.
Wonderful. I've got one last question here. There's been a ton of great questions. We just don't have time to get to them all, so we can maybe continue this conversation in a different way. But are there any already planned out long-term research goals if Perseverance significantly outlasts its planned operation time, like a certain other rover?
Absolutely. Yeah, every rover we've sent to Mars has way outlived its warranty, and we hope that Perseverance will outlive its as well. The nominal mission is 1 Mars year, which is 2 Earth years. But based on the lifetime of Curiosity, we expect that it might have 6, 8, 10, 12, 20 years in it. And so we're planning for those timescales. And we have a long duration mission concept of actually driving up and out of Jezero Crater. One of the other candidate landing sites, one of those top 3, was a spot called Northeast Syrtis that was out of the crater and way over to the west. We can drive to those types of outcrops in just a couple of years after getting out of Jezero Crater. So on a plausible timescale of the mission, we might be able to get 2 landing sites in 1. So fingers crossed for not only a safe landing next Thursday, but for an extended mission so we can make that journey to the west.
Wonderful. Thank you very much, Dr. Rice, for that wonderful presentation. For now, thank you. So turn it over to Dwayne.
Thank you, John. Just so everyone knows, Warren Dunes has music available everywhere. Spotify, YouTube Music, Apple Music, Pandora, Deezer, and iHeartRadio. So go out there and support this fabulous band. As many of you know, it's been a tough time for performers all around the world. So support your local artists as best you can through any way you can, especially this great band that we have for tonight, Warren Dunes. And now coming back to this Zoom stage, let's welcome back Warren Dunes.
Thank you so much, Dwayne, and thank you so much for that fantastic presentation. I feel like I have been spending a lot of the last year shaking my head for things that I'm disappointed in, and today I am just shaking my head in amazement and astonishment at all of the wonderful, truly special discoveries and endeavors that everyone is working on. And so I feel very lucky that I'm getting to hear about these and the specifics as well. And congratulations to your entire team for working on the filter and the camera. That's just really awesome. So we're going to play a song for you right now called Come Find Me. And this is on our band's EP that came out a while back called Welcome to Warren Dunes. Hope you enjoy it. 1 to 10 and 4, 5. 1 to 10 and 4, 5. Take what's wrong and turn it right. After dedicate that to Mars with Perseverance coming its way.
All right, everybody, we're now heading into our last Q&A segment of the night, where Dr. Charles Liu is going to answer some of your pop science questions. So this should be a lot of fun. We really appreciate everyone who sent us wonderful, at times mind-bending questions about science and your favorite pop fiction books, movies, and TV shows. In case you weren't aware, Charles has done some great segments on Star Talk Radio with Neil deGrasse Tyson, which are called Science and Pop Fiction. So be sure to check those out as well if you enjoy thinking about this kind of stuff. I'll post the link to that in the chat as well. We're going to start this segment off with a question about imaginary metals. So Charles, what do you think? In the world of imaginary metals, which one wins in a fight and why? Adamantium, vibranium from Black Panther, or Beskar from The Mandalorian?
I think the best metal is plutonium because it can make you do anything you want, right, in any movie. But no, that's a, oh my gosh. Okay, adamantium is an alloy. It is virtually indestructible and very powerful metal, right? In the Marvel Cinematic Universe, Wakanda there's the sole source of vibranium, which is supposedly the strongest metal, but can also absorb energy and bring it back. So vibranium would be stronger in that case. And then the Beskar metal is supposedly so strong in the Star Wars, the Mandalorians wore them to fend off laser blasts and lightsaber strikes, right? So I think vibranium would win because it can absorb energy and send it back. Theoretically, if it gets hit, it just absorbs it. And the thing is, the old-fashioned original vibranium didn't have the strength properties also that was added in the Black Panther movie, for example. So it would just absorb things, and that has its own properties, but not be necessarily strong. Now, what happened was that Captain America's original shield back in the 1980s was an alloy of adamantium and vibranium, and thus was even more strong and more vibration resistant than pure adamantium or pure vibranium. So that's probably the strongest. The Mandalorians, they eventually were able to be harmed by being cooked inside their, their steel metal armor by this sort of arc reactor that just made it too hot on the inside. That's kind of gross. I don't think vibranium would be susceptible to that, fortunately.
Awesome, definitely noted. Moving into Star Wars, how do you think the Death Star's giant planet-killing laser works?
Oh.
And what kind of power source would be required to shoot such a powerful laser? Could that ever exist?
Oh my gosh. Okay, according to Rogue One, right, which is, some people like it as sort of a way to bridge the gap between the movie sets and some don't. I'm kind of not sure. According to Rogue One, kyber crystals, the same kind of kyber crystals that you put in lightsabers or in blasters, are a kind of crystal that magnifies energy because they're attuned with the force, you see. So you send energy into them, it actually magnifies the energy through the kyber crystals. And then the kyber crystal becomes all that forcey, magic-y thing where they're attuned to the specific wielder of the lightsaber, be it a Jedi or a Sith, that kind of thing. But if you supposedly have 8 huge kyber crystals, and you fire energy from the hyperdrive of the Death Star through these kyber crystal, focusing the same way that you might focus a laser on Earth through crystal, then they all get magnified, they get put together in the center, and then you get that scene in Episode 4, A New Hope, where they blow up Alderaan, right? I don't know. That doesn't seem realistic, I gotta say. In order to blast a planet open like that, I'm not a planetary scientist, but I'm pretty sure you have to do a lot to it. Not to mention that if you actually blew the planet apart, it'd probably just go out and fall back in because it doesn't have enough kinetic energy to send everything out at escape velocity from the center of gravity. But that's for another time.
Awesome. Well, I can sleep a little bit easier at night knowing that, it's probably not possible to blow up entire planets with crystal focused lasers. All right. Next question here. just kind of starting out general, given physics as we currently understand it, is time travel possible, such as the time travel that we saw in Avengers Endgame?
Oh boy. I got all kinds of issues with Avengers Endgame. One of these days we'll have conversations. I mean, I enjoyed it because I'm an old style Marvel fan, you know, thousands of comic books from my teenagehood and all that, but all the plot holes that you could drive a truck through, that's okay. The fan service made up for it. I still had a good time with it with my kids. Okay, so here's the deal with time travel in real physics. The thing about, you know, going into the quantum realm and re-emerging and doing all kinds of other things in different parts of whatever, it's crap, but that's okay. We still like the movie, right? The fact is that you can, in some string theories, imagine a circumstance where dimensions are compactified, in which case, if there is a compactified time dimension, then you can actually cycle through and move in those directions. But then you'd wind up with all these different alternate universes. In that case, the many worlds interpretation of quantum mechanics is almost certainly true. So we have a hard time figuring out exactly where you're going. Now, there were 2 papers published in the past year, in the year 2020, that suggest that if you travel backwards in time, the flow of time actually self-corrects. These are mathematically complicated, and there's no proof of any of it yet. There's no way to experiment with it, although there's some, you know, simulations that you might be able to do. One was sort of the idea of a quantum computer with a qubit. The other was actually going back in time and trying to change an event that might otherwise affect what's happening in the future. The bottom line is they allow for closed loop time travel that doesn't affect causality. It will change things, certain things will go, but it's kind of like a ripple in space-time will eventually damp out, so that if you affect something a year ago with time travel, by the time it gets back to the year where you've left, things are back to where it were. But the way they get there from where they are is not going to be the same.
That is absolutely fascinating and answers some of the other questions that we had in here as well.
Yeah, let me mention that one of those papers was actually co-authored by an undergraduate math student, which is was just working the math. They were coming up with these cool physical insights, much like Roger Penrose, who won the Nobel Prize in Physics this past year, along with Andrea Ghez, about the black holes and Reinhard Genzel. In 1964, Roger Penrose, who you probably heard of Penrose tiling and other mathematical cool stuff that Penrose did, he may be the first mathematician ever to win a Nobel Prize, even though technically there's no Nobel Prize for math. Roger Penrose applied really clever math, including in like a 3-page paper that proved that black holes are a natural result of Einstein's general theory of relativity, when no physicist had yet been able to figure out how to manipulate those equations to show this to be true. Penrose did it in 1964. Pretty amazing.
Wow, well, thank a mathematician. All right, we have time for one more question. So here we go. Let's see if I pronounce this correctly. The Alcubierre drive is becoming a frequently used device to build FTL, or faster than light, capability into a storyline. So in the real world, how would we go about detecting evidence of other civilizations using the Alcubierre drive? What is the radiation signature of the drive? And do our present instruments have the sensitivity to detect such signatures?
Oh, come on. Are you serious? Okay, let me think back. A Mexican physicist, Miguel Alcubierre, was the first person to show that there was a mathematical structure that if you assume that space could be sectioned off in bubbles, sort of like the so-called warp bubble of Star Trek, then you might be able to travel faster than light while you're in such a bubble. So the Alcubierre drive is just a purely theoretical idea where you wind up creating a warp bubble like this, that you can travel faster than light, keeping your ship in it, and just keep moving the bubble along, so that your spacecraft is moving through this particular space as opposed to our space, and therefore can move faster than light, because nothing can move through space faster than light, but you can move faster than light if you're not traveling through space. Space itself, for example, could advance or expand faster than light if necessary. So that's pretty crazy stuff. If such a thing were to happen, and this is a great question, how would we observe it? Well, it would almost certainly create a massive gravitational lens signature. Okay, in other words, if you push a black hole, for example, in front of a star, it will temporarily brighten the star apparently and then dim again. As the object moves through, basically the black hole will curve space-time in its direction. So light that otherwise would not have hit us will wind up hitting our eyes, and therefore the star behind it looks a little bit brighter. You probably get that kind of thing almost certainly. You see a huge sort of wave of gravitational bubbling of space-time. So you could see that. And that, depending on how close you were to that and how bright the objects behind you were, you probably would be able to see it even with modern telescopes. The other thing it would do probably is to create gravitational waves. These days we find them through LIGO and other huge physical systems that are detecting the change in the spatial dimensions caused by, for example, the collision of two black holes. We probably would get some of those gravitational waves as well, but instead of a chirp, a kind of event that you can actually hear if you put it in sound, it would be sort of like a kind of sound. Pretty crazy. I don't know if we could detect that, but where do these questions come from? These are pop culture questions. This is not, I feel like I was just through a thesis defense or something, but hopefully I was able to answer everybody's questions okay.
Oh, that was just wonderful, Charles. Thank you so much for sharing your mastery and expertise with us and entertaining some pretty complex questions. We really appreciate your time.
All right. Well, to quote the Warren Dunes band, their website, it says on there, the sense of wonder and inspiration pervades the music Julia, Jared, and Dominic make as Warren Dunes. They are happiest together on stage, moving and flowing as synchronous aspects of a greater whole. As a performer myself, I gotta admit that sense of wonder and inspiration mixed with happiness, y'all did that tonight. And from the bottom of my heart, thank you, Warren Dunes, for sharing your music with us tonight with the Seattle Astronomical Society. And we appreciate you. So thank you. And now for their grand finale, for the final time tonight, put your hands together and show your love for Warren Dunes.
Thank you so much, Dwayne. And I want to thank Sierra, and I want to thank Aaron and Charles and Melissa and everybody who was a part of this evening. This last song, Aaron asked us specifically to play it. This was from years ago in a band that Dom and I were in called the Five Finger Discount. And I also want to just shout this song out. It's called The Story of the Earth So Far. And my bonus dad, Mike Goalie, is tuning in from Maryland. I know this is a favorite of his as well. So this one goes out to Pops. Hope you enjoy it and have a wonderful, wonderful rest of your evening. 5, 6, 7, 8. Long ago a world was born.
for attending today. Thank you, Julia Massey, the Warren Dunes, Dom, Jared. Thank you so much, Charles. Charles and Melissa, I just can't thank you enough. I almost want to get emotional because I'm just so thankful. And we promise as a community, SAS community, we're going to take your excitement that you bring to science and STEM and Mars and everything else that's going on and spread it to the world. So, and if you take one thing away from tonight, I would say community. SAS, this is a volunteer-run organization. This is your SAS, and so come send us an email, come to our talks, and let's find some community together. And so, Charles, thank you so much. You're like a hero of mine. Melissa, oh my gosh, I can't believe how excited we are, and it's an honor to have you before Mars lands next week. And Warren Dunes, we love you. So we'll end the call, and it's going to seem a little abrupt, and all of a sudden nothing's happening, but we will all connect again someday. Thank you, everybody. Sierra, feel free to hit the end button when you're good. See ya.